25-foot tap rule, as described in the National Electrical Code, does not apply when the tap conductors are supplying the entire load. In this scenario involving the elevator motor, the tap conductors from the shunt trip breaker to the disconnect are indeed supplying the entire load of the 25 horsepower motor. Therefore, the conductors must be sized to handle the full load current of the motor. Given that the motor's full load current is approximately 74.8 amps, the tap conductors must be sized accordingly. Number 3 AWG copper conductors are suitable in this case, as their ampacity is sufficient to carry the 74.8 amps load. Moving on to the fuses at the disconnect, these are crucial for protecting the motor from overcurrent conditions. The National Electrical Code mandates that fuses be rated at no more than 125% of the motor's full load current. Calculating 125% of 74.8 amps yields 93.5 amps. Consequently, the fuses at the disconnect should be rated at 100 amps, this being the next standard size up from 93.5 amps. The 125 amp breaker in the MLO panel serves as the main overcurrent protection for the entire branch circuit and not as a tap point. This breaker is responsible for safeguarding the conductors within the branch circuit itself. Given that number 3 AWG copper conductors are being used, and they have an ampacity of 100 amps after adjustments and corrections for ambient temperature and number of conductors, the breaker should be rated at 100 amps. This is to protect the conductors from overcurrent situations aligning with the conductor's ampacity. In summary, number 3 AWG copper conductors should be used from the 125 amp shunt trip breaker to the disconnect, fused at 100 amps at the disconnect for motor overcurrent protection, and a 100 amp breaker should be used in the MLO panel to protect the branch circuit conductors. Firstly, correctly applying the tap rule is critical. It doesn't apply here as the tap conductors supply the entire load. Secondly, conductor sizing should be based on the full load current of the motor, which is 74.8 amps, mandating number 3 AWG copper conductors. Thirdly, fuse sizing at the disconnect must not exceed 125% of the motor's full load current, requiring 100 amp fuses. Fourthly, the breaker in the MLO panel is a main overcurrent protection, not a tap point, and should be rated at 100 amps to protect the number 3 AWG conductors. Overcurrent protection devices and conductor sizing should always be based on the most recent applicable version of the National Electrical Code, specifically Articles 430 and 240. The 25 horsepower motor is driven by electricity, and this electric motor converts electrical energy into mechanical energy, which is then used to power the elevator. A motor nameplate provides critical information, including voltage, full load amperage horsepower, service factor, and temperature rating. The full load amperage, or FLAW, is the amount of current the motor draws when operating at its rated horsepower and voltage. The motor's service factor indicates the amount of overload the motor can handle for a short period of time. The temperature rating indicates the maximum operating temperature of the motor insulation. The overcurrent protection is essential for safeguarding the motor and conductors from damage due to excessive current. Overcurrent can be caused by motor overloads, short circuits, or ground faults. Fuses and circuit breakers are common overcurrent protection devices. Selecting the correct size of overcurrent protection is crucial. Undersized protection can lead to nuisance tripping, while oversized protection may not adequately protect the motor and conductors. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protection for motors. The motor branch circuit consists of conductors that supply power from the electrical panel to the motor. These conductors must be sized to carry the motor's full load current, along with any applicable dirting factors. Dirting factors account for conditions that can reduce the ampacity of the conductors, such as high ambient temperatures or multiple conductors bundled together. Voltage drop is another important consideration in motor branch circuit design. Excessive voltage drop can cause the motor to overheat, reduce its performance, and shorten its lifespan. To minimize voltage drop, conductors with a larger cross-sectional area can be used, or the distance between the electrical panel and the motor can be reduced. Grounding is essential for ensuring electrical safety and preventing electric shock hazards. The motor, its enclosure, and all metal parts of the electrical system must be properly grounded. Grounding provides a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and de-energizing the circuit. Regular maintenance and inspection of the motor and its branch circuit are crucial for ensuring safe and reliable operation. This includes checking for loose connections, damaged insulation, and signs of overheating. The motor should also be lubricated according to the manufacturer's recommendations. When sizing conductors, the National Electrical Code provides tables that list the ampacity of different conductor sizes and insulation types. These tables are based on specific conditions, such as the ambient temperature and the number of conductors in a raceway or cable. It is important to apply any necessary correction factors or adjustment factors to account for conditions that differ from those specified in the tables. For example, if the ambient temperature is higher than 30 degrees Celsius, a temperature correction factor must be applied to reduce the conductor's ampacity. Similarly, if more than 3 current-carrying conductors are installed in a raceway or cable, an adjustment factor must be applied to reduce the conductor's ampacity. The 125% rule for motor overcurrent protection is based on the motor's full load current, which is the current the motor draws when operating at its rated horsepower and voltage. The overcurrent protection device must be sized to trip at or below 125% of the motor's full load current. This provides adequate protection against motor overloads, while still allowing the motor to start and operate under normal conditions. There are different types of overcurrent protection devices, such as fuses and circuit breakers. Fuses are single-use devices that melt and open the circuit when an overcurrent occurs. Circuit breakers are reusable devices that trip and interrupt the circuit when an overcurrent occurs. Circuit breakers can be reset after they trip, while fuses must be replaced. When selecting an overcurrent protection device for a motor, it is important to consider the motor's starting current. Motors draw a high inrush current when they start, which can be several times their full load current. The overcurrent protection device must be able to withstand this inrush current without tripping. Time delay fuses and inverse time circuit breakers are specifically designed for motor protection, as they allow for a short duration overload without tripping. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Voltage drop is more pronounced in longer conductors and conductors with smaller cross-sectional areas. Excessive voltage drop can cause various problems, including reduced motor performance, overheating, and shortened lifespan. To minimize voltage drop, conductors with a larger cross-sectional area can be used, or the distance between the electrical panel and the motor can be reduced. The National Electrical Code recommends limiting voltage drop to 3% in branch circuits and 5% in feeders. Grounding is the process of connecting the metal parts of an electrical system to the earth. Grounding provides a low impedance path for fault current to flow back to the source, tripping the overcurrent protection device and de-energizing the circuit. This helps to prevent electric shock hazards and minimize damage to equipment. The grounding system consists of a grounding electrode, such as a ground rod or a metal water pipe, and grounding conductors that connect the equipment to the grounding electrode. The size of the grounding conductors must be adequate to carry the fault current. Regular maintenance and inspection of electrical equipment are essential for ensuring safe and reliable operation. This includes checking for loose connections, damaged insulation, and signs of overheating. The equipment should also be cleaned and lubricated as needed. Any damaged or worn part should be replaced promptly. The National Electrical Code provides specific requirements for the installation and maintenance of electrical equipment. These requirements are designed to minimize the risk of electrical hazards and ensure the safe operation of electrical systems. Compliance with the National Electrical Code is essential for all electrical installations. The authority having jurisdiction, or OJ, is responsible for enforcing the National Electrical Code. The AHA may be a local, state, or federal agency. Electrical inspectors review electrical plans, inspect electrical installations, and issue permits. They also investigate electrical accidents and enforce the National Electrical Code. Electrical contractors are responsible for installing and maintaining electrical systems in accordance with the National Electrical Code. Electrical contractors must be licensed and insured. They must also employ qualified electricians who are trained in electrical safety. Electricians are responsible for performing electrical work in a safe and professional manner. Electricians must be knowledgeable of the National Electrical Code and other applicable standards. They must also be skilled in the use of electrical tools and equipment. Electrical safety is everyone's responsibility. By following safe electrical practices, we can help to prevent electrical accidents and injuries. The National Electrical Code is a comprehensive set of standards for the safe installation and maintenance of electrical systems. Compliance with the National Electrical Code is essential for all electrical installations. Electrical inspectors review electrical plans, inspect electrical installations, and issue permits. They also investigate electrical accidents and enforce the National Electrical Code. Electrical contractors are responsible for installing and maintaining electrical systems in accordance with the National Electrical Code. Electrical contractors must be licensed and insured. They must also employ qualified electricians who are trained in electrical safety. Electricians are responsible for performing electrical work in a safe and professional manner. Electricians must be knowledgeable of the National Electrical Code and other applicable standards. They must also be skilled in the use of electrical tools and equipment. Electrical safety is everyone's responsibility. By following safe electrical practices, we can help to prevent electrical accidents and injuries. The motor's full load current, the conductor ampacity, and the overcurrent protection device rating are all critical factors in ensuring the safe and reliable operation of the elevator motor. The interaction between these three components must be carefully considered to prevent overloads, short circuits, and ground faults, which can lead to equipment damage, fire hazards, and electrical shock. The elevator motor is a critical component of the elevator system, and its proper operation is essential for the safety and convenience of passengers. By following the guidelines outlined in the National Electrical Code and other applicable standards, we can ensure that elevator motors are installed and maintained in a safe and reliable manner.